Hi, I'm Alex Zettler.
And I'm Ryan Glynn. For our project, we decided to analyze the stress on a toy skateboard. A typical child skateboard is made of polypropylene, and an example is shown in the image at the top of the slide. Our SolidWorks rendering is shown below it.
Our skateboard has a typical skateboard geometry of 27 inches long by 8 inches wide and is a ½ inch thick. The skateboard has 4 components: the deck, the wheels, the axles, and the trucks, which connect the axles to the deck. The skateboard has a polypropylene deck, steel axles, aluminum trucks, and plastic wheels. We used ANSYS to generate the mesh of this skateboard. For our analysis, we are mainly interested in the stresses in the deck of the skateboard, so we will ignore the other parts. We represent the supports as fixed geometry at the location of the trucks. The load is represented as 2 oblong patches where feet would likely be on the board. Each patch is 75 pounds of force to equal a 150-pound person. This indicates a very tiny-footed man or a fairly fat child. After the analysis was run, we did not think the results looked like they should. We decided this was because the fixed geometry, when a real skateboard would be able to bend at the trucks.
To accommodate this issue, we added the full geometry of the trucks. The trucks have a hole for the axle of the wheels, so we allowed the trucks to rotate around this axis. However, the bottom of the trucks was not allowed to slide out. The result of this was the same as the first attempt, with no rotation of the trucks.
For the next iteration, we include the wheel geometry and the ground. The trucks are able to rotate freely around the axles of the wheels. One set of the wheels is fixed to the ground, while the other is set to slide without friction on the ground. This is why square wheels are acceptable for this simulation. However, it is not recommended that anyone attempt to ride this skateboard on a frictionless plane. We believe these conditions will accurately reflect the behavior of the skateboard.
The analysis of the 150 pounds distributed between the 2 feet is shown on this slide, the result of which is a bowing shape. As expected, the truck's tops rotate inward, allowing the free wheels to slide forward. The maximum stress experienced is 234 psi, located in the center of the skateboard. Although polypropylene's yield strength varies, the 234 psi is well within the lowest estimate of 1,740 psi. The central stress is expected, given that both loads are placed inside of the supports. The further from the center of the board, the less stress is experienced. You will notice increases in stress at the 4 points where the trucks connect to the board. Also note that the neutral axis is clearly seen in the diagram.
Upon further investigation, we realized 2 things. 1, that a person's weight is not always distributed evenly across their feet, but can be concentrated on the heels or toes, for example, when the person is turning. And 2, that Dr. Diaz was going to mark us down for our previous problem being too similar to a beam. To simulate this new scenario, we made a small patch on one side of the deck to run the simulation with.
This analysis returns similar results to the first one. The main difference is the lack of symmetry, as the side of the board under loading experiences more stress than the free end. This forces the board's deformation to twist as well as bow. Another noticeable difference is the higher stress concentrations at the trucks. This is because the trucks on our cheap skateboard are not allowed to easily rotate in the direction necessary to accommodate the off-centered load. This results in roughly twice the stress as in the first analysis, with 472 psi. Again, this is well within the yield strength. Thank you for watching our video on skateboard stress analysis. We hope you learned something about overweight kids riding skateboards. We'd be happy to answer any of your questions at this time.